quantum chemistry, and maybe that's it. But if you have other ideas, I don't know, do you have other ideas that you're interested in?
A little bit about quantum information theory. No.
That's a good idea.
Oh, you mean like channels and things like that?
Yeah.
Entropy and
Yes,
entropy,
yes,
mutual
yes.
information.
Yeah, fidelity of quantum
Yes,
states.
yes,
I mean, those
yes.
are all important things, right?
Yeah, I'm sure they are. That's a good idea. I don't know.
We have not
Information
much
theory.
time,
What?
so we haven't much time to deal with this.
Yeah, that's true. Maybe I should. Okay, I'll think about that.
What did you teach on Tuesday? I'm sorry, I couldn't get out of work.
I don't know what we did on Tuesday. Oh, we superconducting qubits.
Okay.
We tried to cover. Yeah. Okay, so information theory is the request. I'll see what I can do. I've covered it before. It just like no. Okay.
You covered channels, I remember.
No, I mean I've taught it before.
Oh, okay.
Not really this year. Not in this class. Okay. So, but let's start with quantum error correction. And again, actually, this is an area that you could dig into this as much as you like, right? So, I've taught a couple of classes on this, so 50 lectures on this kind of thing. But this is just a brief. These notes are just from a brief tutorial that I did over, I think, 3 lectures. And then if we want to dig in further, we can, or not. Okay, so this is maybe you could say this is the major problem right now in terms of building a large-scale quantum computer. Is that noise is such a big issue. It's hard to manipulate quantum information with high fidelity. And so, for example, if you take Shor's factoring algorithm, roughly, if you look into it carefully, it takes for factoring a k-bit number, it takes about 72 k-cubed gates on about 5 k-qubits.
Oh my God.
Maybe this can be slightly optimized, but so for example, if you're using 1024, which a lot of people use, or 2048, that's what people are using nowadays, I think. You're talking 10,000 qubits ish, and I don't know, 72k cubes, whatever it says there, 10 to the 11 gates on roughly 5,000 qubits. And so if you want this to work, you really need the error per gate to be roughly 10 to the minus 11 in a certain sense, because if a single gate is wrong, so this is just intuitive. It's not. I'm not saying it's rigorous, but if a single gate is wrong, then it messes up the whole computation. Or if you want to make this more rigorous, you could say, so my overall quantum circuit C is equal to the product from J is equal to 1 to 10 to the 11 of some unitary Uj. Ideally. Of course, there's also resting qubits, which I'm not talking about. So there's error on not only on the gates, but also on the qubits that are at rest. But so be it. So this is C ideal. The C noisy is equal to pi j equals 1. Well, I mean, so actually it might be channels, but let's just say uj tilde for noisy unitary. And so then the norm of the error between C ideal minus C noisy. But you can say this is. Have we done this calculation before? Remember? Do you know what I'm going to say? Yeah. Okay. So the norm is just equal to. So what I'm going to say is this. I'll say.
Oh wait, is this the one you break it down into unitaries and then take the norm to unitaries?
Yeah.
I think.
So I'm going to say assume 10 to the 11 is equal to 3, and then take U3, U2, U1 minus U3, U2, U tilde 1 plus u3, u2, u tilde 1 minus u3, u tilde 2, u tilde 1 plus u tilde 3, u3, u tilde 2, u tilde 1 minus u tilde 3, u tilde 2, u tilde 1. So I just added and subtracted, and then I used the triangle inequality.
Yeah.
And everything factors out, so this is u3 times u2 times something, and the same thing times something else. This is u3, and u1 on the opposite sides, so it's u2 minus u2. Yeah, so I end up with less than or equal to the sum from j is equal to 1 to 3 of uj minus u tilde j. So in other words, if you have 10 to the 11 operations, you need each of these terms to be less than, I mean, if overall you want this to be like within 1/100 or something, so or within 1/3, so you get a pretty good constant for the total error rate. You need each of these terms to be like that constant divided by 3, where 3 is equal to 10 to 11. So it's really hard to get errors that are that low. There's no proposed experimental scheme that gets that low. Even these anionic schemes, topological schemes, they're only talking about 10 to minus 5, 10 to minus 4, 10 to minus 6 maybe. And for these other schemes, you definitely don't even get close to that. So maybe you get 1% per gate for 2 qubit gates, and maybe you get 0.1% for 1 qubit gates, kind of thing, in a lot of schemes. So we're probably never going to get so we can run Shor-Zagaloom on a flat quantum computer. We're going to need something else. So there's 2 questions, and I suppose one is you could give up on running Shor-Zagaloom and say, what else can you do? So is there anything interesting you can do with error rates that are like 1% or 2%? And so this is like what the Google people were doing with their quantum supremacy paper. They're trying to come up with an artificial problem that's still kind of interesting and that you can do with noisy qubits. But people are interested still. There's other. So this is called a NISQ. So NISQ means noisy intermediate scale quantum. Noisy intermediate scale quantum computer. So a NISQ device is a fairly small device that we're talking maybe 50, 100, maybe a few hundred qubits that are also fairly noisy. And so the idea of NISQ is of this concept is try to find algorithms that we can run on these devices that already have significant amounts of noise. And so we're not going to be able to do very complicated things with them, but hopefully things that are stronger than the classical computer. So something easier than Shor's factoring out. And so for one example of this is there's some examples in quantum chemistry which are sort of like this. So that's one reason I want to talk about that. Give a lecture on quantum chemistry applications. And somehow they can be more robust to noise in a certain sense. But the other thing is, let's not give up on implementing Shor's algorithm and just try to figure out some better way of building a quantum computer. So we're going to try to actually, let's forget about this. Let's try to figure out how we're going to engineer a quantum computer that has 5,000 logical qubits with very low noise rates. And the idea here is what's called fault-tolerant quantum computation. So in fault-tolerant quantum computation, we have this ideal circuit for Shor's algorithm. And what we do is we compile it by some tricky method into now a larger circuit, a much larger circuit, unfortunately much larger. That now these gates do have noise, but somehow the circuits can handle the noise, and it simulates this circuit. And in fact, this often won't be a circuit. It'll often be a I don't know what the word is really. It'll be some interaction between a classical computer and a quantum computer. So we're doing measurements during. So it's not just a bunch of unitaries. There's some non-unitary operations where we measure part of it and we put that into a classical computer. We think about it there, and then we put it back in. And so this is the idea of fault-tolerant quantum computation. computation. And how does that actually work? Usually what we do is, it's not a black box. What we do is, inside this ideal circuit, every operation is going to be like every single gate, like a CNOT gate or something. We're going to encode it. Every single qubit is first going to be replaced with an encoded qubit. So we're going to use a quantum error correcting code. In this case, one qubit is being mapped into 5 in a certain special way. And then every single gate, like a Hadamard gate, is going to be replaced with an encoded gate, which is important to do that correctly. And then we're going to do error correction after that. And this holds even for like, here I say it's for a gate, but even if you just have a qubit without an operation, so even if it's just resting, that will still be, I guess, an encoded rest operation, which is just nothing, followed by error correction. So even on resting logical qubits, you need to be doing error correction frequently because errors happen. And so this all has to be done carefully. Roughly, though, the goal is to achieve something like what's called a noise threshold. So I'm going to go into details of all this. So I just want to give a high-level picture of what the idea is. So here, the idea is if we start with the distance 3 code. So distance 3 code classically would be something like 0 is mapped to 0, 0, 0, and 1 is mapped to 1, 1, 1, for example. So a feature of this kind of code is that one error is okay. You can correct one error, but you can't correct 2 errors, or you can, but you correct in the wrong direction. So 1 error is okay, which means that effectively the logical error rate is going to be some constant times p squared. If p is the error rate for a 1, yeah, if p is the physical error rate, the effective logical error rate, our goal, whatever that means, we're going to try to define that. But the goal is just make the effective logical error rate be quadratic in the physical error rate. And where this constant is something you can figure out, but some probably fairly large constant. But now the point is, this is Cp squared is less than p. It's less than what you started with, provided that p is less than 1 over c. Is that right? Cp squared equals p. So this point here is Cp squared is equal to p, and so therefore p is equal to 1 over c. Yeah. Okay. So that's this threshold, and so you want this constant c to be as small as possible, so that this threshold is as big as possible. So it's like, and then below the threshold you get an improvement. Above the threshold things get worse. That's bad. And well below the threshold, I mean, up here you don't get much of an improvement, but like down here you get a significant improvement. And so there's I guess there's several ideas here. One is that you can imagine starting with this. So the c really is a constant, like it might be 100. And so then the threshold is 1 over 100, or 1%. And so you can imagine starting here, which is like less than 1 over 100, you get Cp squared, which is here. So then if that's not low enough, if that's not below 10 to the minus 11, you repeat the scheme again to get it down to here. So that's like c to the cube times p to the c cubed times p to the fourth. Yeah. I say it here. Yeah. Okay. And if that's not low enough, you could just keep on repeating. So in principle, you could repeat this as many times as you need, and this error rate. So the error is dropping like p to the 2 to the k, where k is the number of times you repeat this process. So it's dropping doubly exponentially fast in the number of levels. That's good. So doubly exponentially fast error rate reduction means that the number of levels you're going to need is going to be the double log of whatever your goal error rate is, or 1 over that. And that's good because the overhead is also growing exponentially. Because every time you add a level, you have to do this procedure on top of itself. So you take a gate here and you replace it with an encoded gate. That's one level, and then at the next level so this encoded gate is actually made up of 50 different small gates.
How do you encode them?
So, yeah, so each of these qubits you encode it to 5. Each of these gates you replace with this whole procedure. Even in here, you replace each of these gates in here with the encoded procedure. So at the second level, instead of a 5 qubit code, you're gonna have a 25 qubit code. At the third level, you're gonna have a 125 qubit code, and so on. And so the overhead's growing exponentially with the number of levels, k. But that's fine because the error rate's dropping doubly exponentially. So if k is log log, 5 to the k or whatever, some constant to the k is still going to be just log. So it still should be efficient.
If the error is growing way slower than basically your overhead.
The error, the logical error?
Yeah.
Yeah, it's dropping much more quickly, yeah. So this is roughly the idea, and this is something that was studied quite a lot, especially in the early 2000s, late 90s. These kinds of results, they're hard to make because you have to define this really carefully. What does it mean to be an effective logical error, and what does that mean? Because it's a 5-qubit code. I mean, when you have 5 qubits, when you have 1 qubit, you can maybe imagine parameterizing the error by the sum of the error rate for x, y, and z. So you just have like 3 parameters. And maybe you can generalize, or maybe you can just add them up to get 1 parameter. But if you have a 5-qubit code, how many different errors can you have? You can have x, y, and z in each of the qubits, and so that gives you like 4 to the 5 I, x, y, z to the 5 different errors, and you're trying to reduce this down to 1 parameter. So you can draw it on the graph like this. And it's not clear how to make that definition. And then it gets even harder because then you want to make sure that the definition is good. It's good enough that you can recurse the whole thing and repeat a second time. So that's rather tricky, and it took a fair amount of work to get good definitions. Now I think we pretty much do have good definitions, which I will talk about. But actually, a lot of people don't worry too much about this nowadays because nowadays I think most people are rather unhappy with these kinds of schemes because the overhead is still growing too quickly. And so if somebody's actually talking about, like there's papers out there where Google or Microsoft or whoever, they look just in the last year or so, they look at Shor's factoring algorithm and they try to compile it. So they say our noise rates are going to be this, what can we do? Or how many physical qubits do we need? Exactly what the overhead is going to be. And maybe they come up with saying, to get, I think I remember something like, so here, if you want 5,000 physical qubits, 5,000 logical qubits for the encoded computation we're trying to do, on the order of millions of physical qubits for the kind of noise rates that they're studying. But when they do those calculations to get that fairly low overhead, they're not doing it like this with repeated levels of concatenation. At mostly they use either 1 level of coding or maybe 2 levels of coding, but generally not more than 2, because that just becomes very, very bad very quickly. Or they use something totally different that's called the surface code, in which you just do have 1 level of encoding. So I'm going to talk about that as well. But this is a picture that people studied quite a lot in the late 1990s or early 2000s, and it's still of interest because maybe you want to do something that's more than 10 to the 11 gates, like more complicated than Shor's algorithm, and one or 2 levels of concatenation won't be enough. Okay, so the kinds of theorems that prove this kind of statement, they're called threshold theorems. And threshold theorems exist, there's not one threshold theorem, although it's often stated that way, but there's dozens of threshold theorems. And they all say that for this particular noise model, the tolerable, there exists some scheme such that we can achieve arbitrary reliability with only provided that the physical noise rate is less than some constant. And that constant is called the threshold. Because below the threshold, we can compute arbitrary reliability. Above the threshold, I don't know. And a lot of these theorems are very, very vague. Like they just say, here's a noise model. Like an example of a noise model might be, we have independent stochastic polynoise on all the gates. A more interesting noise model might be we have correlated noise on different qubits, but the correlations drop according to the distance between those qubits, drop like an inverse polynomial according to the distance between those qubits, or there's some decay, which is important because if you had strong correlations at arbitrary distance, you couldn't do So those are these kinds of theorems, and they tend to be fairly vague because they often just say there exists some constant. They don't say what the constant is. And the reason they don't say what the constant is because one, it's hard, and two, if you looked into all the details and tried to figure out what the constant was, you just get a rather pessimistic number, like 10 minus 20 or something. So, but nonetheless, these kinds of theorems are useful in principle because they tell you that in principle we can tolerate these kinds of noise models. And even if a theorem does say the threshold is 10 minus 20, what they mean is, I mean, what it will really say is the threshold is at least 10 minus 20. So the threshold could be higher than that, but we're only trying to lower bound it rigorously.
I mean, they're being conservative, basically.
Yeah, they're being conservative.
I mean, that makes sense.
Okay, and right, so that's good. That's good.
I mean, I know you talk, I mean, you talked about this, keeping it, and you often refer to the 5 qubit code. That's the smallest code we know that can correct an arbitrary